Okay, so welcome back to this class. So we are still in the review part. Okay, so let me briefly come back to what we did last week. The definition. So abelian normalized hypergroup. Okay. So abelian normalized hypergroup. So we have the notion of normalizable hypergroup and normalized hypergroup. And remember that when it is normalizable, it's not normalized, but the fact that it is normalizable is equivalent to the existence of a linear character mu1, with which you can normalize the standard element to get the usual sum to be 1 after normalization. And this normalization is noted at the token. So that's okay. So abelian normalizable hypergroup follow. Okay. And here, if you remember in the introduction, we wrote the multiplication law in the dual. But now, if you consider a normalizable, not a normalized, the multiplication in the dual, so the hypergroup structure was in the introduction was stated for normalized, but for normalizable. So you need to write the normalization like that, but as well you can get the multiplication like that. So this is exactly what we want. Okay. Okay, and so in fact, the unit for this multiplication in the dual is exactly this linear character. And so the proof is straightforward. So again, I skip the proof because we are in the review part. So this is the unit, and this corresponds also to, when you are in a fusion ring, this corresponds to the Frobenius-Perron dimension linear character. Or it corresponds to the first column of the character table, the first table where everything is positive. Okay. Okay, so here we are just saying that we can define also the involution in the dual exactly as we did in the introduction, but up to putting some renormalization given by the linear character. So, okay. So you put the normalization like that, but you can reformulate, you can put it out, and so you get this constant. Okay. Particular if mu1 maps to real, this is 1. Okay. Okay. Now, so I will try to go quickly as possible, otherwise it will take too much time for this review part. So the order of a normalizable hypergroup. So this notion generalizes the notion of Frobenius-Perron dimension, global Frobenius-Perron dimension of a fusion ring, or it generalizes the notion of the order of a group. You just take the sum of the square of the character degree for group, or the sum of the square of the Frobenius-Perron dimension of the basic element for a fusion ring. And here you take the sum of the square of the complex modulus, and you need to have this extra constant, which was, if I'm not, I star 1 inverse. This constant is 1 in the fusion ring case, but for hypergroup in general, you need to have this constant. Okay. Okay, so in the abelian case, following all by equation 2.5. Equation 2.5 was, if I'm not mistaken, equation 2.5 was the first or the second isomorphism. So 2.5. Why is 2.5? This kind of here. the first orthogonality relation, which is here. Okay. So you have a kind of orthogonality. It's like a inner product, and you get some orthogonality relation. And now I should not do that because now I forgot where I was. Here. Okay. So if you apply, in fact, you apply the orthogonality relation, but with I equal j. And so you get that. And so you get exactly that the first formal codegree is the order of the normalizable hypergroup. Exactly when you are in a fusion ring, the first column of the character table, the square norm is exactly the Frobenius parent dimension, and this is the formal code, the first formal code. Okay. So this notation will be simplified like that. When there is no when B, the basis and the linear character is implicitly understood. Okay. Okay. So in the normalized case, we have okay. In the normalized case, so if you have a normalized hypergroup, in fact, there is nothing to normalize. So the linear character is already 1 everywhere. So you have 1 everywhere. So this is 1. So you just have the sum of these constants are the order. Is the order. Okay. Okay. So if xi are the basic element of the hypergroup, the application of this specific linear character to this xi is what we will call the di. So in a fusion ring, this is called Frobenius parent dimension, the basic Frobenius parent dimension, the Frobenius parent dimension of the basic element. Here we have the hypergroup, we have the standard element, but this is the same notation. Okay. Okay, so what about? So in the normalizable case, you apply the formula for the dual we mentioned 5 minutes ago, and you get that, in fact, yeah, like that. So you take any mu g is another linear character, not necessarily this one, and you get this formula. Okay. You apply that, so it's okay. So we say, okay, so the notion of weakly rational, weakly integral is exactly as for fusion ring. Weakly means a property of the global Frobenius parent dimension. So here, a property of the order. So we say it's a weakly rational or weakly integral if the order is rational or integer, exactly as for fusion ring. But for a fusion ring, the Frobenius parent dimension, the global Frobenius parent dimension is always an algebraic integer, so rational implies integral. Okay. And for a fusion ring, when you say it is integral, not just weakly integral, but integral, it means that all these di are integer. So it is stronger property. The converse is false. You can have weakly integral which are not integral, because we have this di can be square root of some integer, and then when you do the sum of the square, you still get an integer. Okay, so okay, so we wrote a formula for the dual fusion coefficient. So this notation is more intuitive. So the fusion coefficient in the dual it was this notation. In the literature, in fact, it is more usually use this one. That's why it was used, but for the intuition for us, it's better to use that. So we have this formula. Okay. Okay, so we wrote a formula for the normalized case, but for the normalizable case, here it is this formula. So what is the difference? Okay. So I don't remember the formula exactly here, but the difference should be there. I guess this is the difference. Yeah, this should be the difference. In fact, in the normalized case, everything is 1, so you don't have this coefficient. Okay. So for normalizable, you have this coefficient, but this is, okay, the formula for the dual fusion coefficient. Okay. Yeah. Here I wrote, so in the normalized case, you have only that, but for the normalizable case, this number is renormalized as this number. Something like that. Even if, okay. Anyway, I don't remember the formula here. I don't want to go back to 2-1. It will take too much time. Okay. Now, okay, so you take an abelian normalizable hypergroup. Okay. Yeah. So this lemma is saying that the order is independent of taking the dual, stable by dual. Okay, so you have the normalizable hypergroup, you have an order, you have its dual, you have also an order for its dual, but this is the same. Okay, and the proof is here. So again, I skipped the proof in the review part of the last semester, but the proof involves so the formula for the dual fusion coefficient. Yeah. And you use this H, this HI in the dual, it's like that, etc. So it's okay. And finally, you get the same. So you start from that. Yeah, this is normalized already, so it's just the sum of this HI in the dual. And this HI has this kind of formula, etc., etc. So it's okay. So the next proposition holds for any normalized hypergroup. So here we don't need to assume the hypergroup to be abelian. Okay. So you take normalized hypergroup, you define this F1 like that. So F1 is the idempotent corresponding to this linear character, mu1, which was called augmentation map in the introduction, but it is just the mu1 corresponding to when you discuss normalizable, but here it's already normalized, so the mu1 is already 1. So the idempotent corresponding to this linear character, to this algebra morphism here. Yeah. So we already discussed that. So you have this idempotent. So for any f equal, okay, so this proposition is just saying that the idempotent corresponding to this linear character has this formula. Okay. Okay, so we know, so again, I skip the proof, but in fact, we already know that it decomposes as a sum of that because this is a basis and some coefficient. So this is what you do. You start by doing that. And then I have to skip, but if I try to see what kind of ID, there is a trick here. There is a commutation. I don't know. Yeah, there is a kind. Yeah, you use here. There is a kind of. This is an egg. There is a kind of. You can see Fi as an eigenvector for this operator with this eigenvalue. It is explained here. Anyway, so I skip. Okay. So we have the formula for the normalized case, but for the normalizable case, you have the same kind of formula. The difference here, so you have hi star, di star, xi. And here you have only hi star. So you have a di star, additional di star. Because it's normalizable, okay? And so you just take the normalized case and you apply the previous formula and it should be okay. Okay. Now, so you take, and so as I said, we did not use abelian somewhere. So you take a normalizable hypergroup. Okay, so this proposition is saying that the order is not just invariant by the dual as we proved before, but it's also invariant by rescaling, which may be important. Okay, so you rescale and you apply and you see it's working because the rescaling, if you rescale the basis, you also need to rescale this constant, and this will vanish. So it's okay. Okay. So in particular, so the order of a normalizable hypergroup is equal to the order of its normalized version. The normalized version, you put another line like that. Okay, so now we come back to abelian case. Abelian normalizable hypergroup. Okay, so now we provide the formula for the formal codegree in the dual. So the formal codegree, so this is a normalized hypergroup, and there are also formal codegree denoted like that on the dual, and in fact, this is this formula. So here I expect it's hi, not ni, but I need to check whether it's really. So this is a proof. Hi, I guess. Yeah. So we have this kind of formula for the formal codegree on the dual. I don't remember if you have formula for the formal codegree. We have the here. What was the formal codegree here? Was just the square norm of the each column. So the square norm of you fix algebra linear character and you take the square norm. But I did not remember if we get a short formula like that. But at least in the dual, you have a short formula like that. So in fact, I guess if you use that, you can get a formula here by considering the dual. In the dual, it is the same. And if you put hi like that, and here you need to put the dimension of the basic standard element in the dual. Anyway, so the proof is there. Okay. So here we use this kind of identification. Remember the evaluation map, which is the linear character on the dual. It's identified with, in fact, the element like that. So, but we need it to be normalized. It's not just we want something normalized. Okay. So I skip the same. we define this tau bar and we define tau. So because the formal conjugae are defined as the decomposition of this tau, we have tau bar, etc. So here we get it is exactly this idempotent, etc. So I skip the proof. Finally, we get that. Okay. So what is about this? What is this remark about? So you take an abelian, maybe rational. I'm not sure we need normalizable hypergroup. In order to find the central primitive idempotent on the dual, we can apply. Then define tac. Okay. I skip this remark. This kind of technical remark related to notation. Okay. So now, corollary. So now you take an abelian normalizable hypergroup. Okay. So this corollary is saying that you take the primitive central idempotent of the linear character corresponding to this element, so the unit in the dual basis of the dual basis is the element in the dual, which can be written like that. So only involve the linear character and the formal conjugae. Okay, so you use the fact that we prove that in the initial hypergroup, this is tau hat. So in the dual, this is tau hat hat. And you have to be careful about the notation again. But this is similar to what we did before. Okay. So again, there is a warning about the notation. Okay, so maybe before I use these two notation, but now I use this two notation for the. Here, this is for the primitive central idempotent in the hypergroup or in the dual. Okay, primitive central idempotent. Okay. So this corresponds to this linear character. This corresponds to this linear character. So linear character, there is a primitive central idempotent corresponding. Okay. Bye. So fix this notation. This corresponds to this. This corresponds to this. Okay. Now. Okay. So what's this definition? Morphism of normalizable hypergroup is a morphism of hypergroup where which agree with this linear character. Okay. So now Frobenius-Perron theory on real non-negative hypergroup. Frobenius-Perron theory. So this section is interesting in the sense that the Frobenius-Perron theory, which it's applied in fusion ring theory. In fact, the Frobenius-Perron theorem we use in a fusion ring theory do not use the full, not completely use the Frobenius-Perron theorem because the Frobenius-Perron theorem involves matrix with positive entry. But fusion ring, the fusion matrix are positive integer. So in fact, from the Frobenius-Perron theorem, you can prove more than what you get in fusion ring. In fact, you can prove something in fusion in hypergroup, where you replace the fusion coefficient, replace integer by real, in fact. So maybe this is what I am saying here. When you say real non-negative, by real non-negative, then you can apply Frobenius-Perron theory. You cannot apply Frobenius-Perron theory on hypergroup without this assumption, because then we don't have a matrix with positive entries, non-negative entry. Okay. So this is exactly what I am saying here. Okay. So you can apply this theorem and you can define the notion of Frobenius-Perron dimension. And in fact, as I said, basically this is also a linear character, and this is basically this is exactly this mu1. Usually, mu1 will be the Frobenius-Perron dimension. But you need the Frobenius-Perron theorem to get this linear character. Positive. Okay. So we did not. Okay, so this is the eigenvalue of the fusion matrix, multiplication by that. So this is L2 matrix norm of this fusion matrix. Exactly as for fusion ring. Okay. In fact, this Frobenius-Perron dimension do not depend on. In fact, this is a linear character, and we know that in a linear character, but we know this is non-negative, so we have this equality because the complex conjugate of this is real. The complex conjugate of real is itself, so you have equality, and in fact, it's more than real, it is non-negative. Anyway. Okay, so hypergroup is called symmetric if we have this property. In fact, we already mentioned that in the introduction. So symmetric, so you take A, B, you decompose it as a sum of standard element with coefficient. And the coefficient for one is the same when you decompose BA. So this is symmetric is specific to the coefficient of the unit. Okay. Okay, but by definition of this constant, remember this is A star 1 inverse. You already know that symmetric can be reformulated by the fact that this constant is invariant by taking the evolution. So this is also a way to state symmetric. Okay, symmetric, and in fact, if I am not mistaken, as I said in the introduction or before, I said the hypergroup has a structure of Frobenius algebra in the classical sense, and this is also, if I'm not mistaken, the analogous of symmetric Frobenius algebra. If I'm not mistaken, okay. So, in the abelian case, everything is symmetric. Because in the abelian case, you can commute this and this, so it's trivial. But in general, in fact, we will prove, we will more or less prove that the symmetric assumption is true in general. So under maybe some finite dimensional assumption, we need finite dimensional. But in the hypergroup we define in the course, it was already assumed finite dimensional. Maybe you can define some infinite dimensional hypergroup, but here it's already finite dimensional. I guess any finite dimensional hypergroup is symmetric. I don't think there is an extra assumption, but we will see that soon. So any finite dimensional hypergroup is a symmetric Frobenius algebra, in some sense. Particular, any fusion ring is a symmetric Frobenius algebra. Okay, so general. In general, if so you take a general hypergroup and you take some general ijk, and if this fusion coefficient is non-zero, then you can get this equality in terms of the hi constant. And in fact, the pose is when? It's 5 or I never remember. When is the pose? 4, 5. It's like 5. Yeah. So if you assume this assumption, you can use the associativity assumption to get this kind of equality. So you apply the associativity, you reformulate the associativity in terms of the fusion coefficient, okay, you take t equal 1, etc. And then you take t equal 1 to force to get something related to this constant. And then, okay, you reformulate and you get that. So you get that. You get this first step. You iterate that again. You apply here. And you get that. And again, you get that. So you came back to what we start from. So you apply again, you came back to that. And so you can multiply all the intermediates and you get 1. And why you need non-zero? Because if it is 0, you cannot say this is 1 because 0 equals 0. That's why you need 1. So you get okay. So this theorem is new. It was not in the version 10, but maybe and now it's in the new version. It should be. If I guess now if I'm not mistaken, so we should remove that because now the version on archive is version 11 or 12. So this theorem now appear in the online, but when I did this part last semester, it was not yet appeared. In fact, it appeared because when I prepared the class, I realized that we can prove that symmetric is true in general for finite dimensional hypergroup. Okay. So if you remember in the beginning of the section, we defined this function tau, which was so this tau is symmetric because in fact the fact this implies this tau is symmetric. Okay, without having abelian. Here it's general, only finite dimensional. And so the proof, in fact, we use this lemma. And so I will skip the details of the proof, okay. 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 So this corresponds to this equal this, so you have this equality. This equal this, no problem. So now, this proves this last sentence, and now if you want to prove that, okay. I will skip the proof. So let me see if I can catch some idea. Okay, so we reformulate the previous lemma like that. Demonstrate that. Oh yeah, there is a kind of. You can reduce to get a root of unity. So in fact, you apply some power and you get 1. What was the thing? You can reduce to a system of equation where the root are root of unity. Okay, so it's a bit tricky. But because it's finite dimensional, in fact, this sequence should be finite because you recover, in fact, because the index you recover taking power n mean you need to find to get a new index. So because it's finite dimensional, you have finite many index. So it means that this set is finite. So it means this set there is some cyclicity here. So this means that you have a power source. You have two powers which are equal, two different powers which are equal, and so it's not zero. So you can simplify and you get a root of unity. Okay. And so this is the idea. You use finiteness. You need finiteness and root of unity. Okay. So it's very nice. In fact, this term is new. I guess it was not so much known, at least not known to us in the literature of hypergroup theory. A finite dimensional hypergroup is symmetric. So we did not find this result in the literature. So the proof is not so complicated. So it should be known to some experts. Maybe it's written somewhere, but we did not find. Okay, new assumption on hypergroup. The rest of we assume. Yeah. So this is also, you have to be careful in the definition of hypergroup. Even in the introduction, we did not say how the involution deal with the product, because in fact, everything was defined in term. We just say there is an involution, but up to now, in fact, if you define everything in terms, if you define this involution, if you define everything in terms of a star algebra, and this involution comes from a star algebra, then you have this kind of thing. But if the algebra is not a star algebra, if you are not in the star algebra framework, you just need to assume that the involution really work like that. So it permutes, the involution of the product permutes like that. And it can be reformulated in terms of fusion coefficient like that for all ijk. And ijk is nj star, I car, k star. So you cannot deduce that from the definition, but in fact, what you can deduce the Frobenius reciprocity from that. In fact, so this now is assumed. This is usual. This is not an assumption. It's not what I say. Okay. For fusion ring, for example, this is already assumed, and you can. So let us prove the Frobenius reciprocity exactly like that. So the Frobenius reciprocity for fusion ring, there is no coefficient. Everything is. But the Frobenius reciprocity is saying that you take the dual of that, and then you have to permute these two coefficients. Here you have the dual of ij, you have I star, but k and g was permuted. And so you can also apply again here, and you permute these two, and again here, you permute these two, again here, you permute these two, again here, you permute these two. So if you iterate the Frobenius reciprocity, you get an equality between 6. But the idea is that when you apply the dual, you permute. And in fact, this is a reformulation of the fact that the dual corresponds to the adjoint of the fusion matrix. because the adjoint of the fusion matrix, I should have written, I may have written that. From this reciprocity is exactly meaning that the dual corresponds to, so the fusion matrix of the dual is the adjoint of the fusion matrix. But here you have to be careful, you have to take care about some coefficient because we are in hypergroup, not in fusion ring. Okay. So the proof. Okay, so the proof require this anti-evolution definition assumption, and this kind of equality we proved before. Okay. Yeah, so it's reduced to that. So for this reciprocity, this is very important because you have, when you consider the fusion coefficient, when you consider this fusion coefficient here, you say, okay, this is equal to this one. So you only need to consider this one, for example. When you are interested in classifying fusion ring, for example, you need to classify all the possible fusion coefficient of some sequence of some types of some sequence of basic formulas per dimension. You have a sequence of basic formulas per dimension, and you say this is called a type. Say, okay, I want to classify all the possible fusion data giving this type. So you need to classify all the possible formulas coefficient like that. But because of this equality, in fact, you can divide by 6, more or less, the number of variables you need to solve. So this is very useful. Anyway, okay, so here we prove explicitly that the Frobenius per dimension is invariant by dual. Okay, so here, okay. So the proof involves the fusion matrix. Okay. So taking, okay, so if you put this coefficient here, you get this equal to this with a ratio. So this is exactly here. And then, okay, so here, this is what I said. The fusion matrix of the dual is the adjoint of the fusion matrix. Here we only need to care about transpose because everything is real. But because we are in hypergroup, we have to care about some renormalization. This is a renormalization matrix. Okay. And then you know that the Frobenius per dimension is the square norm, the L2 norm of the matrix. And okay, so you is equal to that. And D, so yeah, we will make the pause. So let me just finish. So you can remove the D by this argument, by some eigenvalue, etc. And so this is the Frobenius per dimension of the dual. So we get this equality, and we can make the pause now. Pause. On. Okay. So, we reviewed that. Okay. So Frobenius per dimension is invariant by dual. And it corresponds to the fact that the fusion matrix of the dual is adjoint of the fusion matrix. Here it's transposed because everything is positive, is real. And we need to put some renormalization, but it's okay. So here, this sentence is saying that, so all what we said before was about real non-negative. You can apply Frobenius-Perron theorem for real non-negative. So you get the Frobenius-Perron dimension, which is the L2 norm of a matrix, so it's positive, and which is exactly this property. So you take that equal that, you get this property, which is exactly the property we need to be normalizable. Remember, normalizable is equivalent to the existence of a linear character whose value is positive on all the standard elements. So, for real non-negative hypergroup, the Frobenius-Perron dimension is the perfect candidate for the linear character to get a normalizable structure. Okay, so in particular, every real negative hypergroup is normalizable. Okay, so it's symmetric. We know that it's finite dimensional. So the symmetric assumption is already satisfied by this theorem, so we can avoid. We can automatically use this property everywhere. Okay. So what this remark about? The hypergroup is transitive. Okay, so we have a kind of transitivity. A transitivity is a property involving the fusion coefficient. So for all index, you can find two other indices such that this and this are non-zero. So this transitivity is saying that two index can be related in some sense by non-zero fusion coefficient in that sense. So, okay. So if you have two index, they always exist. So the second index appear with a non-zero coefficient, appear as a component of the first index multiplied by something on the left and on the right. Like that. Particularly if it is abelian, you only need this. But I have a small doubt whether we should put J and I. But anyway, by Frobenius reciprocity, we don't need to care about these kind of details. Okay, so why it is always transitive? So you pick, so you know, you take I and J. So you know the product of a standard element I star with the standard element G star as a kind of decomposition. So you can take two index which are non-zero like that, and you apply Frobenius reciprocity, you get that. Okay. This is non-zero by Frobenius reciprocity, we get that and that, which is non-zero, so it's immediate. Yeah. So this is what I said, in fact, in this note, but so maybe this note is not should not be written here. It was an overview of this. But as I said, we can apply the Frobenius parent theorem, because real and negative, you have a matrix we are non-negative entry, so you can apply Frobenius parent theorem, which is stated here in generality in the EGNO book. Because it only involves real and negative matrix and not integer, non-negative integer matrix, but yeah, real and negative is enough. Okay, so this is really a algebra morphism. Linear character. This is what I call linear character. Algebra morphism from H to C. Okay, so this is the Frobenius parent dimension. Okay. So here I realize that in fact, in the initial definition of normalized, the initial definition of normalized do not involve a linear character, but just involve existence of a normalization with some property about the unit, etc. And then we prove that normalized is equivalent to the existence of a linear character. So maybe this sentence is not in advance. We just say this can be the coefficient you can use to get a normalized initial definition. But if we use the theorem we proved normalized equivalent to this to be a linear character, the theorem we proved before automatically proves that this is a linear character, as long as you have some positivity here. But more or less, basically, somewhere you need to apply the Frobenius parent theorem because you need the positivity or something like that. Anyway, doesn't matter. So we really have this linear character, which is take positive value on the standard element. Okay, so you define the Frobenius parent dimension of a real non-negative hypergroup like that, exactly as you did for in fact, the sum of the square of the Frobenius parent dimension, the basic element. Here, it looks like the definition of the order, but in fact, this is what we will state here. Okay. Okay. So we already proved that the order is independent of the normalization. And so we get that, in fact, the order of the hypergroup is exactly the Frobenius parent dimension in the real non-negative case, because we need real negative assumption to define, to get the Frobenius parent dimension. So in the real non-negative case, you can always take mu1 equals the Frobenius parent dimension, and you can always take the order to be the global Frobenius parent dimension of the hypergroup. Okay. And in the normalized case, the Frobenius parent dimension is always 1. Okay. Okay. Okay, so as I said, invariant by rescaling, etc. Okay, so you take a real and negative hypergroup. Yeah. So it's also invariant by rescaling. Okay, so we know. So what was the point? We know that the Frobenius parent dimension is that this is invariant by rescaling. So this is also invariant by rescaling. So why we have to prove something here? I don't. So it's not clear to me why we need a proof here, but better to have two proof than to have zero proof. So, okay. Maybe it reproves this. It uses exactly this proof, but apply specifically to this. Okay, so don't care. Okay. Group-like element. So group-like element correspond to, in the fusion ring case, it corresponds to the element with the Frobenius per dimension equal to 1. Here, it will be more or less the same up to some constant. This structure constant in some sense of the hypergroup. In the rest of the paper, all abelian real and negative hypergroup are normalized by that. Normalizable. Therefore, okay. So the dual of normalized is normalized. So if all the normalized correspond to that, because the dual of normalized is normalized, in the dual you also take that. Okay. For any real and negative hypergroup, you have this. So you take di to be the Frobenius per dimension of the standard element, and so you have this is always greater than or equal to 1, and it will be equal to 1 if and only if we have that, which mean, and this will be the case, the group-like case. This means what? This means that you have a standard element, you multiply it by its dual, and the decomposition only involves the unit. So it's like, it's more or less, look like you have a group element and its inverse, you get the unit. So every element going this way will be called group-like. And in fact, we will show that the product of two group-like is also group-like. Yeah, the product of two group-like will be another group-like, satisfying that. Okay, so the proof. So you first need to show the positivity. So you decompose that, but you focus on the unit here. You apply the Frobenius per dimension. Okay. Okay, real and negative assumption. So I guess we get an assumption. In the definition of hypergroup, you know that this is positive or non-negative, etc. So you get this from the definition. And then if it is equal to 1, you will get this is 0 everywhere except for this part. And so you get there's only a single component. And I raise an if and only if, so you can get the other way, but the other way is straightforward. So okay. If you apply that to fusion ring, you said that a basic element multiplied by its dual is equal to the unit if only if the Frobenius per dimension is equal to 1. So where did we involve the dimension here? Yeah, here, dimension equal 1. Okay, so that's okay. Because in the fusion ring case, this is 1. So you have d square equal 1, but di is positive, so di equal 1, etc., etc. So as I said, the set of group-like elements is exactly the set of standard elements satisfying this property, or satisfying this property, because by the previous lemma, it's the same thing. And okay, and we will show that it has a group structure. Okay. So in the normalizable case, not norm, because here I guess it's normalized. Real and negative hypergroup, no, not normalized. So what about this? In normalizable, suppose that it's normalizable, then this is there. If only if, no what? We can, yeah. So applying that to the equation 1, I'm lost. I was here, okay. So for normalizable hypergroup, we establish this is a group like if only if we have that. Okay. So which is exactly this. Let me second here. Or this. Yeah, so you apply. You know, hi is equal to the inverse of that by this equality. So you put the inverse of that here, so you get that. Okay. You just have that. Now you apply the Frobenius Perron dimension here, and you get that. Okay, so I don't know where we are going here. So we have that. Okay, but it was already written here, so I don't understand what we are doing here. Anyway, we have that. Really, it's to prove the equality. I don't remember. It does not matter. Okay. Okay. So an element is group-like if only if. So here it's a reformulation of being group-like, which is neither that, neither that. It's a reformulation which involves the linear character. So it is group-like if only if the complex modulus of the linear character, any linear character applied to the this normalized thing is always 1. Okay, so this maybe it was a point. Anyway, always 1, in particular for the Frobenius Perron dimension, but that should be contained here. Okay, so okay. So in particular, yeah, so we have a group-like element in the current table. The line, the row corresponding to a group-like element always have something, at least in normalized case, always which is a root of unity, because again we have everything is algebraic integer. So an algebraic integer of modulus 1 is a root of unity. Anyway, so this is equivalent to being group-like involving all the linear characters. The proof. So you have an if and if to prove. If you assume it is group-like, yeah, so I excuse the proof again. So you apply this. Yeah, it's more or less group-like. It means very close to the unit. So yeah, you apply this equality here, and this is a linear character. So it's an algebra morphism. So you can decompose everything, and you use the fact that you have the complex conjugate when you apply the dual, etc. And conversely, if you have that, so it works. So it's okay. Okay. So you have that. So you have an equivalence formulation for a group-like element in the hypergroup. Now you can you can have the dual version. You take the linear character as an element of the dual, and if you apply the previous lemma, you can state exactly dually, but here, so you have this element is group-like in the dual, if only if you have the same kind of equality, but here this should be true for all standard elements. So it should be true for all this. In the previous case, it should be true for all this. The formula is the same, but for one, it should be true for all such this. And here, it should be true for all such this, because this is the linear character of the dual. This corresponds to the linear character in the dual. The dual of the dual. Remember, if you identify H with the dual of the dual, then this corresponds to an algebra morphism, the evaluation of xi divided by di, etc. So it's okay. The same proof. This is exactly what I said. Okay, so now in an abelian normalizable hypergroup, you take any group-like linear character. Then for any group-like linear character, the corresponding formal category is the order. Okay, so it is which is equal to n1. So the formal category and is the same as the Frobenius of the Frobenius parent. Here it's not assumed to be real non-negative. So the same as the first. And the converse should be true, I don't remember. Okay, so you apply the previous lemma and the first orthogonality relation, and you get an equality. Okay. So now, you take an abelian normalizable hypergroup such that only one of the following holds. Okay. So, such that it is real non-negative and mu1 is the Frobenius per dimension, or the dual is real non-negative. Remember, this property, real non-negative dual, in the fusion ring case correspond to B3 positive. So it corresponds to this papers with Liu Jiangwei, Jisong Wu, myself, and Ling Shuang, when we define the notion of 3 positive. It corresponds to have non-negative coefficient in the dual. So, one, this or this. If you have this or this, then you can prove that the value of the complex modulus. So, in fact, the complex modulus of the entry of the character table is dominated by the first column. You have the character table, you have the first column, and you take the square modulus. It's not always, in this case, this is always positive, so you don't need that, but in this case, you may need the modulus. You take the first column corresponding to mu1, and you take the modulus everywhere, and it is saying that for every other column, the modulus are always dominated by the first column. This is exactly what it is saying. And remember that the equality hold in the group-like case. Okay. So you have this kind of result. So can I catch some idea in the proof? The first case, you assume it is Frobenius per dimension and real negative. Okay. can I catch some ID here? We use this trick we already used before, the fact that this idempotent, is a eigenvector for this multiplication matrix, for this eigenvalue. Yeah, so in fact, yeah. The point, as I said, this is the idea of a character table. What is a character table? You have the fusion matrix, which can be simultaneously diagonalized, and the diagonalization entry are that you use that to make the character table. And so this idempotent are the eigenvalue vector for this diagonalization, for this anyway. So you use this kind of trick, and yeah, you use linear algebra eigenvalue eigenvector. So now, if the dual is real or negative, what can I catch? What ID can I catch? Okay, so you have this kind of decomposition. It should be. Yeah, so I skip the proof. I'm not able to catch any ID. Okay, so under the same assumption as before, so this or this, so real negative on the hypergroup and that or real negative on the dual, under the same assumption, we have that we can prove that, in fact, the formal category are less than the order, and it is equal if and only if the element is group-like, exactly what I expected. So the fact that the formal category corresponding to a linear character is equal to the order is equivalent for this to be a group-like element. And this is same kind of ID, same kind of proof. So I skip. You use again the first orthogonality relation, etc. Okay. Now, so you take a real and negative hypergroup, take the normalized version with the current dimension of the standard element, as usual. Okay. No. But if you restrict this to be the group-like, then this set form a group. Once after normalization, you take a group. Okay. And in this group, the inverse is taking the dual. Okay. So this set is not the set of all the standard elements. It's not the set of all the normalized standard elements, it's the set of all the normalized group-like standard elements. And this form a group with this inverse for this element. Okay. So group-like element is that, and it's just a check. You just have to check. You use this definition and you check, and it should work. Okay. So it's not so trivial. Okay, so here we know that it's group-like, so we have this kind of, it decomposes only on the unit. So it means that you have something which is non-zero here. Okay. Yeah, so the proof is quite long. It's longer than what I expected. But as I said, I skip. Okay. So the proof is one of the longest proof up to now in the course. So it's not so trivial. But I guess the proof is well written here, so it's not complicated to understand. You can read again. Okay, so the last step is to prove that if you have a group-like element, this dual is also group-like. Okay. So it's not complicated, but it's not short. You need one slide. Almost you need 2 slides for the proof. But I think all the details are written here. There is no difficulties to read the details. Okay, so we denote this set of normalized group-like elements like that. So we denote by that the above group of normalized group-like elements. Okay, so what was the statement here? Form a group. This form a group. Okay. So this group is denoted like that. Okay. So you start from the hypergroup, you get the group of group-like elements. So you have some normalization. So if you start from the normalized version, you get exactly the same set, etc. Okay. Okay. So dually, you apply the previous result, but on the dual. So you take an abelian normalizable hypergroup such that the dual is real and negative. Then the set of group-like elements in the dual is also a group for exactly the same reason as before. Okay. Okay. It corresponds to the group-like. So here the group-like element. So I have a bit. I'm a bit confused about the notation. Let me check. Normalize group-like element like that. Okay. And here. Okay. No problem. Just the normalized basis. Okay, so now you take a real non-negative hypergroup. You take an element, a group-like element, and this lemma is stating that the product they are also product of 2 normalized group-like elements is a normalized group-like element. But this is strange. Why don't we use this to prove this previous lemma? We did not use that. So this form a group, but we did not prove if this set form a group, in particular, the product of 2 are already there. Or maybe we use this next lemma as an intermediate lemma here, and this is strange. By lemma 22, I don't know. I don't know why. Maybe here there are less assumptions than before. Real and negative. No, same assumption. I don't understand. So just now, I don't understand why we prove that. It's more or less the same thing. There may be some subtlety I am missing, but if we prove that this set of objects are from a group, in particular, the product of 2 are also there. I don't understand. Anyway, maybe I'm missing something, but in fact, the proof is not so short. Anyway, so you take an abelian real and negative hypergroup and a linear character such that you have so this, what is that? This is, so it's almost the Frobenius-Perron dimension, but up to a root of unity, up to something of modulus 1. So you assume for this specific M, so you have M and N. So for this specific M and N, this linear character is exactly as the Frobenius-Perron dimension up to a constant of modulus 1. Okay. And this theorem is saying that it should be the same for P, for any component of the product, in the product of this and this. If this is true, then for any component here, the component means something with non-zero coefficient, you also have the same result. So you decompose, you apply this linear character, and maybe the result followed by some positivity. In fact, you use, here you apply a trick which will be applied many, many times in the course. You write a sequence of inequality, and then you realize that what you have in the left is the same as you have in the right. So all the intermediates should be equalities. And so in particular, you can have some, you can say something about the components. Every component should be equal because you have some inequality here. So this equality should be an equality, and so you have that, and it's okay. So this is the ID. So here I provided an ID, so I can skip the rest. Okay. So I guess today we are. I was quicker than last week, so we really advanced. We did not lose too much time. Okay, so now you take an abelian real and negative hypergroup. Then, okay, so the same. So here I explain why this is not covered by. This is not covered by what we said before because because this is not assumed to be real and negative. You just assume the hypergroup to be real and negative, and then the set of group-like elements in the dual is a group. In this lemma, we needed this to be real and negative in the dual. So this is, you have something new here. And this lemma will use this kind of trick of the previous lemma. You have two elements satisfying this property, almost Frobenius-Perron dimension up to a constant of modulus 1, and it is the same for the component. So the proof will use that. So you start from two things like that. Root of unity, okay. So you make the multiplication of these two linear characters in the dual hypergroup. So okay, now you have this multiplication. It's like that. Okay, so you apply. So you decompose inside. You have the component we are looking for. So we know we have some. You have this, okay. Now, what we are doing, so you replace this inside the previous equality, you get that. Okay, so you get something like that. And on the other hand, you use a definition of the product, because here we did not directly, I guess. No, what are we using here? On the other hand, you have that. So we normalized. Okay. And this is equal to that by definition of that. When you apply to normalize, the definition of the product is like that. So what did we use here? Well, we use a normalized, okay, but on the component. So here we first developed and then apply the definition on the component. Here we, okay, so we apply that here, make the product, you get that. Okay. So you just, in fact, you are just reducing, you get something here, and then you compute what you need to be equal to in the statement, or what you need to be equal to. So you compute something else, and what at the end you realize that you get the same thing, and so you have an equality, and so you have this equal this. So okay, so this is an element. This is a basic element in the dual, okay, and it is group-like. So okay, so I skip the details. Okay, so you have an abelian real and negative hypergroup, a linear character, a group-like linear character. Then, if you multiply any linear character by a group-like linear character, you get a linear character. Okay. And it is not covered by some previous level because we don't assume that also again. Okay, so yeah, so it's yeah, it's almost time. So what? So I think the proof here is all the same thing. You want to prove something. What you want to prove reduced to an equality. You compute the left-hand side in some way, you compute the right-hand side in some other way, and you realize that in fact they are the same. That's why you have some on the other hand, because you compute the left-hand side in some way, the right-hand side in some way, and you get some equality. And so what you wanted to prove reduced to you have this equality. You prove that the left-hand side equals the right-hand side just by computing that in two different ways. Okay. So we get that, in fact, this can be reformed, and maybe I will finish by that. This means that intuitively, more generally, in fact, the set of group-like elements act on the basis, because when you multiply an element in the basis, it's still in the basis. So the state. So when you take two group elements, you multiply two group, you have group elements. But when you generalize, when you consider hypergroup or fusion rings, the multiplication of two elements is not a basic element; it's the sum of basic elements. You have you have something more quantum in some sense. But you can also recover the notion of group-like element, where it's an element what you multiply by another. Multiply a group-like element with another group-like element, you get a basic element. So and this philosophically is saying that it acts. So a group-like element multiplied by a basic element is also a basic element. So there's some classical aspects are about this group-like element. Okay, so I guess I will stop here. because it's time. Yeah. Right. So this was this action is stable by complex element. And the dual of that we formulate as okay. So tomorrow I will come back. I will start from here, and I will maybe read again the statement of this two lemma, of this that and that, to show in what sense it's a dual version. But okay. So section 2, we are in page 78. Yeah. So we almost finished the subsection 2.4. Okay, so see you tomorrow.